And so now I would like to talk about what's coming in Go 1.3 and our plans for development beyond that as well. For those of you who weren't here earlier today, my name's Andrew Gerrand and I work on the Go team. I live in Sydney, Australia, and I work with some of the Go people there. And yeah, I've been doing this for about 4 years. 4 years as of yesterday, actually.
Happy birthday.
My Google-versary. So Go 1.3. We released 1.2 at the 1st of December last year, and our release schedule is a 6-monthly thing, and so we will be going into a code freeze on the 1st of March, which is not a code freeze, it's more like a feature freeze. It's don't do anything stupid freeze. And that will continue until the release date of June the 1st. Now that date may come forward depending on the stability of the system, but that's kind of a conservative timeline. Alright, so what's happening? There's a to-do list. After Go 1.2, the contributors got together, we sent out some mail and said, hey everyone, tell us what you're working on and we'll write it down in a doc, and then we can prioritize and figure it out. Because last time we just kind of tried to just do everything at once, and then it was kind of a bit disorganized. So we have a plan this time. So that link is to that to-do list doc. This talk is based on that list. It's an aspirational list. Definitely not all of it will get done. So we'll see. So one of the key things is we now have 100% precise GC, or as close to as is practical. And that means people on low memory systems, on 32-bit architectures, won't see the pathological memory leaks that you would see sometimes in some programs. So that should make some people happy. Doesn't matter to me personally, but some people are pleased by that. Also on the topic of precision, we're working towards a plan for having copying stacks in Go 1.3. Previously we had a stack split, segmented stack approach. So when you created a Go routine, it would have a fixed size stack. As you needed more stack space, another stack segment would be allocated, and you would have effectively like a linked list of stack segments. Unfortunately, while this is a nice design that's easy to implement, it has some pathological cases where you may have stack allocations and deallocations in a hot path of your code, and it kind of would strike at mysterious times depending on seemingly unrelated changes, and it was very hard to diagnose and work around if you ended up in that situation. So the copying stack approach is instead, when you run out of stack space, we allocate a new stack space, copy the old stack to the new one, and rewrite all of the pointers inside that stack. And one reason why it's more difficult is we need to fully understand all of the types of inside that stack so that we can rewrite the pointers. And working towards the precise GC has enabled us to do this. And so there's a nice document at that link that explains the rationale for contiguous stacks and how it will be implemented. This is a graph from that document that shows the JSON benchmark in megabytes per second using an experimental contiguous stack approach in green versus the existing segmented stack approach. And you'll see that the performance is better or on par, depending on the initial stack size that we're setting. So you can see when the stack segments were quite small, we were getting a lot of noise, and it would fluctuate wildly depending on where that stack reallocation was happening in the code. Okay. Sugu mentioned Dmitry earlier, Dmitry Okov. He's a great hacker. Actually, he maintains a website called 1024cores.net, which has a whole lot of information about multiprocessor programming. But he's been working already on 1.3, and these are some of the changes that are already in and their ramifications. Lots of CPU time savings, shorter garbage collection pauses, faster scheduling and go routine creation and so on, memory savings, and there's a lot more coming. He actually gave a talk about what his plans in October last year, but then I couldn't find the slides, so I should have mailed him about that. But there are hints that he's going to do a rewrite of how channels work, so that should really benefit any kind of concurrent programs in Go. And another feature which has been added already is the sync.pool type. And its purpose is to provide a generic free list that the runtime is aware of. Now, because Go is a garbage collected language, usually you don't really have to worry about memory management until you do. When you end up in, for instance, if you have a web server which on each request needs to create a buffered reader to read in that HTTP request. If you're servicing many requests per second, then you're going to allocate one of those buffered readers for every request, and then as soon as the request is done, you're going to stop using it and it will be garbage collected. Now, as your throughput increases, obviously the number of garbage collections is going to increase. You're going to end up with latency problems and so on. And so the solution was to put a little free list inside your code. So you could have an object pool in the form of a buffered channel, say buffered length 10, and when you need a new one of those objects, like a buffered reader, you would, this is just kind of like pseudocode, I mean it's real code, but you would have some concrete type there, not just object. You would call a function like the object function, and it would use a select statement to attempt to receive an object out of the pool. If it succeeds, it just returns that existing object, otherwise it will allocate a new object. And then, so you would say, do this, use the object key, and then you would put it back in the pool when you're done. So once you've service the HTTP request, you put it back in the pool, it can be used by the next incoming request. And so the object put would attempt to put it back in the pool if there was space in the buffer. So the result is that in like a high throughput system, you can reuse, you have these kind of global free list caches of objects to save reallocation in high throughput situations. And there are a bunch of these in the standard library. There were a bunch of them in code inside of Google and in open source projects as well. And so Brad kind of really pushed for the sync.pool type to be introduced. And what this is just a general version of this thread safe list. And so you can create a sync. This is exactly the same code. It's exactly the same functionality. You create a sync.pool. You give it an optional function to construct whatever the value is in the pool, and then you can just call the get method and the put method to treat it in exactly the same way. Now, the major benefit of sync.pool, besides being general, is that the runtime is aware of it, and so the runtime is responsible for emptying that pool when appropriate. And at the moment, we're emptying it on garbage collection. And so all of those little caches that exist in various libraries can be replaced with pools, and that means when a GC happens, all of those pools just get flushed out. And that just relieves the sort of steady state memory usage of many programs. You don't have these pockets of allocated free lists sitting around. But it is an experimental type. It may not be released. We're waiting to see how code changes as a result. Probably many people in this room would have no use for this. Does anyone feel like they would use this? So there's a few, right? And that's what I would expect. There are some specific situations where it's useful. And so if this does appeal to you, if you're running a tip, please let us know if you're using it or if you intend to use it, so we can use it as an argument as to whether we should include it or not. Okay. Also, one big feature of Go 1.3 is support for native client. Who knows what native client is? So a lot of people. Basically, it's a binary verification mechanism. So you build, it's so that you can prove that a blob of x86 or now ARM code is not going to do anything unpredictable. So the original use for it was to run compiled binaries as part of Google Chrome. So you'd have a website that would send you a binary, and you can run it on your machine because you know that it's not just going to delete everything. So NACL, as it exists in Google Chrome now, it uses a binary format called PNACL, or Pinnacle, or Pinnacle, or something. And that is pretty closely tied to LLVM. It's a defined format, but it's something that you have the Pinnacle code, and then it can be compiled to Intel 32-bit or 64-bit or ARM. But the Go NACL port does not target that format. Instead, we generate the NACL verifiable machine code. And the reason for that is it was a lot easier for us to target the machine code approach because we're already generating machine code and doing it pretty well. What our compilers produce is very distant from what the Pinnacle kind of LLVM intermediate format is like. So we currently have support for 32-bit and 64-bit Intel architectures. NACL does support ARM, but we don't support it yet, and I'm not sure if we will. But the major significant use of this toolchain already is in the Go playground. So if you visit this website and you can run code and it's compiled and executed on Google servers somewhere, we use the NACL toolchain to sanitize those programs effectively. And you can too now. So the NACL toolchain includes the same fake time network and file system capabilities that are in the Playground's compilation toolchain too. And I think as a use case for that, you could imagine writing a coprocessor for a database so that you can execute Go programs as part of queries on remote servers, say. There are so the native client port qualifies as an operating system port, and there are other operating system ports. There's SunOS, which Aram is going to talk about in the next talk. Dragonfly BSD is ported, but we don't have a maintainer for it, so we're not sure if we're going to keep the code, unless, is there any Dragonfly users here? Well, so that kind of explains the problem. But if it goes, that's fine. Plan 9 is still not finished. I guess it's a research project. And there's possibility that we'll see ARM support for Darwin and Android at some point. Possibly this cycle, maybe next. But obviously those are more significantly difficult. We're looking at making some changes to the Go command, in particular to improve build times. So when you build a Go program, it first has to walk all of the source, to find all of the dependencies, and then it has to stat all of those dependencies to see if they have changed since the last compilation. And as a result, aside from linking, the biggest chunk of any build is that analysis process. And so the proposal is to add this Go background command, which launches a daemon that will monitor your Go source files and use something like iNotify or whatever the various file system change notification interfaces are on the various operating systems to watch those source files change. And it maintains an in-memory data structure of all of those source files and all of the information required to build. And then when you build, the Go command just asks that daemon, what's up? And the daemon says, not much. And it's like, no, I want to compile it. And so it tells it what's changed. So all of my programs talk like that. I don't know why. And so to support this, we are adding a FS notify package under OS to the standard library. That's the idea. And there's a proposed interface in discussion here. There are already a few FS notify packages. There's one in the Go tools repo, I think. There's a couple on GitHub, and they're all varying degrees of popularity and feature sets. So we have a very small interface being proposed there. So if you have a use for this, you might want to go and check out that CL and chime in if it doesn't do what you think you might need. We're also hoping to add support for linking against Objective-C. So in 1.2, we added support for linking against C++ using CGO. So you could write a CGO package that has a little a little Go wrapper around a little C wrapper around your C++ library, which sounds terrible, but it's better than writing C++ code. And
better than Swig.
It's better than Swig. That's absolutely true. Yes. And the same thing works in theory with Objective-C, and in fact I've seen, there's a guy in Japan who actually built a little library that wraps around Cocoa, and you can open native Windows under OS X, but he had to hack the toolchain a bit to make it happen. But we hope to open that up this round, and that will make it easier to work in the OS X and possibly iPhone kind of sphere at some point. A common complaint people have about Go binaries is that they're pretty big. The main reason for that is that they're statically linked. But if you look, Rob kind of got annoyed and compiled a Hello World program against Go 1.0, 1.1, 1.2, and found that the binary size has almost doubled in that time. So why is this? Because we keep adding debugging symbols and other tables of useful information to support various tools, but really it's time to rationalize how all that stuff works and do some deduplication and make it all work a bit better. So we intend to do that as part of some work on the linker, and that's where the linker overhaul comes in. So the GC toolchain, which is the one that comes with the standard Go installation, is based on the Plan 9 C compiler toolchain. So Plan 9 was designed with many different architectures in mind. It had to be very portable. And as a result, they have this design where your C compilers and your assemblers, they generate not machine code like GCC does. It generates this kind of intermediate assembly language. And then the linker reads in all of those libraries when it's loading and translates that intermediate language into the machine code for the particular architecture. And it was a convenient design, and it was convenient for us at the beginning. But what it means is that the linker is actually doing some of the work that conventionally the compiler side would do. And so the linker becomes more of a bottleneck when compiling. Because you can compile many packages in parallel, but you can only link once. And so the linker is a bottleneck, and we want to address that. So if you look at what the linker does now, it translates the intermediate pseudo instructions into real machine instructions, and does some relocations. And a list of those relocations. And then the second part is it deletes dead code, merges what's left, handles relocations, and generates some data structures and so on, and generates the final executable object binary. But so the plan is to take that this step and extract it into a liblink binary, and in fact that's already done. And so in Go 1.3, that part of the compiler, the linker, has been moved to the compiler, Go compiler, C compiler, and assembler. And so the intermediate object format is changing and will actually include machine code. And so now the linker only does the second part of that. It actually becomes quite a simple program. And since it's become so simple, it actually means that we can rewrite it in Go pretty easily. And once we rewrite it in Go, we can use Go routines and so on, and channels and so on, to parallelize parts of the linker stage as well. So that should yield some significant performance benefits relatively easily. So this brings me to the final major thing, which is starting in 1.3, but will probably take a couple of releases to be fully realized. And that is an overhaul of the compiler entirely. And so as I mentioned, it's based on the Plan 9 C compilers. And that's all written in Plan 9C. The assemblers, C compilers, and linkers were all taken wholesale. The Go compilers are a new C program that fit into that toolchain. But it would be better if we had a Go compiler written in Go. Now the reason why we started with C then, in the beginning, is because Go didn't exist, and bootstrapping a compiler in its own language is difficult even when the language is stable. But when you're actually actively developing the language while developing the compiler, it creates fiendish bootstrapping issues where you have to have several versions of a compiler whenever you change language features and syntax and so on. But today, these concerns aren't really an issue anymore because Go does exist and it is stable now. So now we're looking at having a Go version. The benefits of Go are pretty obvious. Go is a better language. It's easier to write and debug. If we didn't think so, we wouldn't all be here now. Go has better tooling support, better modularity support, and so on. And probably the most important thing is that Go programmers are more likely to work on the compiler if it's written in Go. So currently being written in the Plan 9 dialect of C, and in a particularly idiosyncratic style of that, really limits the appeal of getting into that code base, because you either need to be prepared to learn a lot of idiom and style, or be the people who are already doing it. So we're hoping to attract a lot more interest in the compilers and optimizations and so on by having it in Go, because it's more fun. So the plan is not to rewrite the compilers, because we've already invested a significant portion of our team's time in the existing compilers, and it's a subtle thing to get right. Instead, we're going to translate the C compiler to Go, and we're going to do it automatically. So we'll actually develop a translator to compile it to take the C code and output Go. So the 5 phases are to develop and debug this translator, to translate the C code into Go, and then delete the C code immediately. And the really nice thing about the first stage is we can develop the translator over a long period of time and still work on the C-based compiler at the same time, because we don't have to worry about skew between the translation and the original. We can just do the second stage in one fell swoop. And then we intend to clean up and document the code, adding unit tests to really verify what the code does, before going on to stage 4, which is to profile, look for hotspots, optimize, re-architect, refactor, split it into packages, so on. And the final phase is to replace the front end of the compiler with the front end packages like Go Parser, Go AST, Go Types. And that will probably necessitate new versions of those packages. It's already felt by most people that, and probably you've noticed, I don't know, that Go AST and so on are not really enough to write a decent compiler. I don't know. Maybe translate it to another language is one thing, but generating machine code is another, I guess. I say that not knowing anything about it myself, not having done it. So as far as bootstrapping issues, obviously now in the future, if you download a Go source binary, a Go source tarball, you're going to get a bunch of Go code, and if you have no Go compiler, what do you do? The plan is that the compilers for 1.3 will be buildable with 1.2, and 1.4 with 1.3, and so on. And so the bootstrapping process will be a matter of building each successive release of Go. But you only need to do it once per machine. You have a shell script that'll do it automatically, so it takes machine time but not human time. And obviously you keep the old binaries around so you don't have to do it over and over again. But since that scales badly over time, obviously if we get to Go version 1.20 something, instead we can write a backend for the compiler that emits C code, and we can check those C sources in to the repository, and then you can build with a C compiler as you do today. So a few alternatives. Why didn't we decide to build new compilers from scratch? I was already kind of mentioned that we've spent at least 10 man-years of time working on the existing ones, so it would be a shame to throw all that away. And also it's not really that well tested either. Like, it's not like we have a really, really thorough set of unit tests that test every single aspect of the compiler. So it would be fraught with danger to do a rewrite, I think. Why not translate the compiler manually? Well, for one thing, who wants to do that? It's not going to be me. And as I mentioned earlier, you can continue to work on the existing compilers in parallel with an automated approach. Why not just translate the backends and use Go parser and Go types and so on immediately? Well, that's not really tenable because the APIs are already very different between the existing compiler and those front ends. And finally, in the million-dollar question, why not discard the current compilers and use GCC Go or LL Go or something like that? And the main reason why we wouldn't do that is part of the beauty of working on Go, I think, is we have this quite a simple foundation that we're working on. We just have this simple tool chain that's well understood. And we're able to move very independently as a result. And we have a lot of flexibility. If we had to tie ourselves to a really substantial, large other project like GCC or LLVM, it would certainly slow us down. It would certainly add a lot of complexity to our release process and so on. Alright, so that's the compiler overhaul. There's also going to be lots of other small things, which I can't really discuss here because they're either too small or they haven't happened yet. But there'll be a lot of them, so stay tuned for those. And thank you very much. So I'm happy to take questions.
Yeah, about translator, how far do you want to take this project? Should it be a general translator?
Yeah, so
for all C code? Or?
Yeah, so the question was, how far do we intend to take the C to Go translator as a project? Yeah. The idea is that we'll write it specifically to translate this code base to Go, and that's it. But that it doesn't mean that we're going to hide the code away and not share it with anyone. It'll be there for people to use and extend. And there's been so many people have asked me that same question that I fully expect there'll be sufficient interest to spin that off into some kind of project. Yeah. But definitely the initial goal is simply to translate the code that we have, which, you know, it won't support the full C spec. You know, we only use a subset of C's features anyway, for instance, and we don't really use macros.
But the output should work. There's no adjustment needed.
Yeah.
Okay.
We hope so. Yeah. Other questions?
Dimitri is going to rewrite channel implementation, you said. Are there any plans to make channels work over a network?
The question was, are there plans to make channels work over a network? The answer is no. We used to have a package called NetChan, you probably remember. It was taken out because it didn't really seem that useful in the end. Rob felt it wasn't the right interface. I personally think that it's kind of futile to do network channels because the semantics of channels guarantee you certain things. So like if you're working, if you do a send on a channel, you know that if it sends, it's either in a buffer or it's been received by someone in the process. But there's no, once you introduce the network, you want to understand things like, oh, I sent, but then it disappeared somewhere in between. Or, you know, there's all this kind of other semantic goop that is much more complicated than the channel semantics. And so by that point, you might as well just write a new API. And that might be the net package or RPC or something like that.
You can look at a package from Tumblr called Go Circuit, and that has hacked up the Go runtime to allow you to basically spin off Go routines onto other machines. And I think that's probably about as close as you can get.
Well, also what Peter demonstrated this morning with Iris is more what I would have in mind as something that's kind of like using channels, but it's really just a nice abstraction over talking to clusters of machines. And I think that's generally more useful. It's rare that I can't really see how channels fits. It works well in process, but I don't know about it. I should take one more.
Are there any larger changes to Go, except for those you're talking about query for the later future?
Are there any other changes to Go?
Bigger changes.
Bigger changes, like to the language, or?
Yes, something like that.
So there are no. The question was, are there any bigger changes slated for this release or other future releases?
No, for future releases.
Well, for future releases, not this one. So
This one.
if you look at the to-do document, is Aram here, by the way? The next speaker? Because I can go over time if he's not. All right. If you look at the dreams section of the to-do doc, that's stuff that's not happening anytime soon. So.
Did Dimitri do 2 of those middle ones?
Oh, did he? Or maybe he did. I don't know. This was last updated in November, so it's possible that it's done already. I would really like to see the ability to use Go programs or Go libraries as shared objects linkable from other languages. That would be really cool. And there's no reason why it can't happen, it's just a matter of work. So I think it will happen at some point. I showed the VFS stuff in the talk 2 talks ago. I'd like to see some VFS stuff into the standard library in a more standard way, but it's not really being felt like there's a good solution to that. But yeah, I don't know. It's really whatever people feel like working on. As far as the language itself, I don't see any big language changes coming anytime soon.
Is there any discussion about adding generic language?
There's plenty of discussion.
So is there nothing like actually wrote down?
No. But it's still something that people talk about in the community, and it's something that we talk about on the team as well. It's not a forgotten topic, and it's not something that we refuse to do. It's just a matter of finding the right approach. Cool. I'll just take one more. Yeah.
Are there any plans to support loading shared libraries into the Go programs or to?
Yeah, so the question was, are there any plans to support dynamically loading shared libraries? And the answer is yes. The same person, it's Elias Naur, is doing the Darwin ARM and Android ARM ports, has been experimenting with that. I think that's one of his end goals. And we're supporting him in getting there. But there are, that's dynamically loading libraries from other languages.
Or from Go?
But from Go, there are some. We're not sure how that would really work out because of initialization order depends on some things. So it's not really clear how that would interact. But the work he's doing is loading non-Go shared libraries, I believe. So that's, yeah. Cool. All right, thanks very much.